Thank you, Mr. Chairman, for the introduction. My name is Gianluca Megna, and in this presentation, we are going to see how to eliminate wheel and rail wear and damages using a new wheelset arrangement for metro vehicles. May I have the timer? Thank you for the help. Okay. Running in a curve at a slow speed is always a nightmare for a vehicle equipped with bogies. A big amount of energy is dissipated at wheel-rail contact due to both lateral creepages and longitudinal creepages. So this results in wear, high amount of wear and damages. And one of the solutions to overcome this problem is could be lowering the yaw stiffness of the primary suspension of the bogie. But it is not always a suitable possibility because if we need stability at high speed or if we have traction, as very well explained in some of the works by Stuart Grassi, from which the title of our paper is inspired. If we have traction and very low yaw stiffness of the primary suspension, the behavior, the curving behavior of the bogie is dramatically reduced. So it's difficult to find a compromise between steering, stability, traction, and this is especially true in metro lines where sharp and steep curves are often found and the traffic is almost homogeneous. So how we can reduce creepages? Independently rotating wheels can be used to eliminate longitudinal creepages, but we know that it is not a suitable solution for bogies, and it is applied only on trams. Lateral creepages can be eliminated with steering systems, but it's difficult to find a reliable active steering system or passive steering system. So to our knowledge, the most diffuse steering system is the one adopted by Talgo trains, that it consists in a single wheelset with independently rotating wheels guided by the car body, by links from the car body. So it is a very smart solution. You can see it in the picture there, but however, it has some very particular arrangement for the bearings and for the suspension. It allows to have a low floor train, a fully low floor train, but there is no space to put motor inside. So traction is always concentrated in locomotives. So in what consists our solution is there are two independently rotating wheels that are supported by a straight axle, so no rotating axle. There are two linkages that generate the steering system from the car body, just like a Talgo, and then we can directly flange a motor on the wheels for each wheel. So we can generate a direct drive transmission. Obviously, here you can see a sketch of the solution, and it is to show the overall dimension of the motor. It is not the right place to discuss about the design of the wheelset, of the choice of the motor, but it's important to say something about that. Preliminary checks show that torque can be reached starting from the existing motor that nowadays are very diffuse, quite diffuse for electric cars. So these motors are installed directly in the hub of the wheel. There are some open points. We are evaluating that, but they will discuss in another paper. Most important in this kind of solution is the driving strategy of the motors. we know that with ATO system, we know exactly where we are constantly. So we can generate, we can design a very simple design, driving strategy, with a speed control on straight track and a torque control on curved track. So it is very simple without going in the detail of the control design. So also from a architecture of the vehicle point of view, we can do some improvements applying this kind of solution. In fact, with some constraints, for example, the total length of the train or the maximum axle load, we can have a lower number of wheels. We can have shorter and wider car bodies, and we can have lower fully loaded mass. So on the right, you can see the sketch of the entire length of the vehicle, and the first axle and the last axle are connected by cross bracings. So also in this solution, all the wheels can be motorized. So to investigate the behavior of this new solution in terms of wear numbers, some multi-body simulation were performed. Different scenarios were evaluated, but the most important one is the simulation of the starting condition in very demanding situation in terms of curve and slope. So a falling friction, a very simple falling friction model was implemented, and the torque has been increased until the slipping condition were reached. So the first, we can see here the first important results, that the torque that can be applied to the new solution, to the new wheelset, is until reaching the slipping condition is twice the torque that can be applied to the conventional one. So better characteristics in terms of performance, starting acceleration can be reached. Here we can see a video, a short video. There is the track. The vehicle is entering into the curve. Here we can see the lateral contact creep force on the first axle of the bogie. All the bogie behave in the same way, and longitudinal forces, contact forces on the rear axle. So the vehicle will stop naturally from the effect of the slope and the rolling resistance, and then torque is applied to simulate the starting condition. The same was applied to the new vehicle. I have to skip because this is very long simulation, because due to the lower rolling resistance, the train take much lower time to stop. So you can see that it's until running, and then traction is applied. However, you can see that in curve there is no creep. There is traction, there is no creep, lateral creep force or longitudinal creep force. So going to the results, this is on the right. You can see a schematic representation of the behavior of the bogie. Blue arrows are lateral T gamma values, red arrows are longitudinal T gamma values, and they are pointed in the direction of the tangential creep force that lay on the plane tangent at the wheel rail contact. So it is a schematic representation of the whole simulated scenarios. So I think it's very impressive, and is useful to understand the energy dissipated at the wheel rail contact. The T gamma values reach up to 500. So there is a comparison between the two vehicles. In particular, we have the first bogie of the conventional vehicle have a reduced train set of the new vehicle. We can see that in the second case, almost all the wheels have a T-gamma. If you look at the ball number, the T-gamma are always lower than 10. Many of them are 0, so there is no damage introduced by that wheel. We have some higher values up to 100, but they are related to the first and the last car body, so in the whole train set, their effect is negligible. While in the second way, for the bogie vehicle, this number are related to all the bogie in the train set. So here we can see the result for all the train set. So the difference in the total wear number is astonishing. In the worst case, for the new vehicle, we have 1,600 against 6,000 wear number, total wear number. So it's very impressive, the behavior. And there is no damage introduced by the new vehicle at balance speed. So the simulation have been performed also for different curve radius, not only at 200, that was the curve that you have seen in the videos. There are relevant advantages also in mild radius curve, not only in very sharp curve. And up to 100 meters, we can see the advantages. So, going to the conclusions, we have seen how it's difficult to find for a metro vehicle a compromise between steering, stability, traction. Independently rotating wheels are not suitable for bogie, and therefore a single axle guided independently rotating wheel was proposed to eliminate longitudinal and lateral creepages. Direct drive can be easily applied to this kind of solution, and the advantages of what we call gearless driven guided independently rotating wheels are very impressive, and we have shown how wear numbers can be dramatically reduced by using this solution. So going to the statement, no wheel rail damage is forecasted by using the innovative gearless driven guided independently rotating wheel architecture. Thank you for the attention.